can verify your code with. And after you verify your code, you're going to be able to go further and compute and solve the entire homework. So alpha, beta, and gamma. Just one sec. This is the animation, okay? So for example, this is alpha, direction from maximum principal stress to the north. Beta, vertical angle from the north to the direction of maximum principal stress. Notice that that would be, for example, what kind of stress regime will be that? Maximum principal stress is vertical. That's a normal, right? That's a normal. This one, let's move it a little bit. This is strike slip. And in order to make it reverse, you need to make this S3 point. Oh, I already had it there. So, well, no, actually this is reverse, right? S3 is here, S1 is here, and S2 is there. You got a question?
So in the notes you have tau, d, and tau s as well.
Yes.
How do those differ from the tau we discussed?
The taus, and this is also over here, tau d, tau s. On this same plane, if I draw the plane again, normal to that plane, I'm going to have Sn or sigma n, whichever you want to look at. On that same plane, as we have defined this coordinate system over here, if let's say this is tau, the component of tau in direction of the strike is tau s, the component of tau in direction of the dip is tau d. And actually this is quite important because, for example, if you have a shear stress, as it says over here, that on this plane you're applying a shear that is going in that direction, that means that if you have two blocks, what is called the hanging wall, which is on top of what is the fault, will be moving up. And if you had the shear going in this direction, it will mean that block is moving down. And this one is going to tell you in which direction it's moving. It's moving like this, or if it's moving like that. All right, yes?
Can you explain the top term equation again? What's the vector before?
This vector over here?
Yeah, but this equation, what's the vector?
So I was meaning with this to have this vector t, that will be an effective stress vector, and this will be a total stress vector. Because notice that here I am multiplying the total stress tensor, and here I'm multiplying the effective stress. Oh, yes, that was the confusion, right? So this SG, that's the stress tensor in the.
The last vector, and there should be normal.
Yeah, should it be dot n sub n instead of dot n? Yeah.
Very well, thank you. So how do you calculate then since you were asking about tau d and tau s? we know how to calculate Sn or sigma n shear stress. Tau deep is going to be just the vector n times t. So it's going to be t dot product. This is not going to be a vector actually. It's just a value. Times which vector do you think over here? N t, right? And tau s is going to be t times n s. And t times nn gives you Sn, the three components of the vector t. So probably we can now complete this plot. So if I go a distance Sn over here, this one is t. Okay, so let me see if I'm missing something from the homework. I have added some uncertainty in the homework. And I like that when you generate randomly distributed fractures, well, that's going to be random, right? But then later, I'm giving you some uncertainty. I like you use a normal distribution. So the uncertainty in that case is going to be one standard deviation. So instead of just plotting a single point, you will see like a cloud of points near those orientations. And I think that's it. That's it for today. The due date is going to be Monday next week. And on Thursday, we're going to start talking about linear elasticity, okay? Kinematic equations and constitutive equations. All right? Okay. Thank you, guys. And I'm going to look at your homework